Welcome to the Explainer. Today, we're tackling a battle that honestly happens at keyboards around the globe every single day. We're talking about the massive push and pull between writing incredibly clever, highly idiomatic code versus writing code that a human being can actually sit down and read without getting an instant headache. We're diving into a really fascinating micro case study from the blog Notes-on-Haskell-Programming by an author named Ang. We're going to break down exactly what happens when absolute brevity and mathematical soundness collide head-on with the real-world need for clarity. And that brings us right to our core question. Which actually matters more, writing idiomatic code or writing obvious code? It's a question that hooks into a frustration I think literally anyone who has ever collaborated on a software project can relate to. You know the feeling, right? You open up a file, look at a single line of logic written by a colleague, or let's be honest, maybe written by yourself 6 months ago, and you realize you have absolutely no idea what it does. You just sit there staring at your monitor, your coffee getting cold, realizing you have to dissect this complex logic puzzle just to understand the basic flow before you can even start your actual work. That tension between what is technically elegant and what is practically obvious is exactly what we're going to unpack today. So the crucial point is really captured by our source author, Ang, with one foundational rule, and it's this: code is read significantly more often than is written. Now, I know it sounds simple, almost like a cliche, but it is absolutely the bedrock lens through which we need to view today's entire explainer. Just think about the life cycle of a code base. When you type out a clever or elegant line of code, you write it exactly once. But over the lifespan of an application, that exact same line is going to be read dozens, hundreds, maybe even thousands of times by different developers trying to fix bugs, add features, or just untangle the system architecture. The reading to writing ratio is completely lopsided. If you're optimizing for the writing process instead of the reading process, you're ultimately optimizing for the wrong thing entirely. All right, let's move into section 1, the cost of clever code. Okay, let's dive into this because we're about to look at code that demands some serious extra mental translation. When we prioritize brevity, you can't just scan the code. Your brain actually has to stop and perform a decoding step before you can even begin to understand the business logic. Let's look at this micro case study in Haskell to see it in action. We're comparing two different one-liner approaches to solve the exact same problem. On the left side, we have what Ang calls the data-focused approach. It reads, return $, maybe body, anthus, body, amthus, idiomatic. Over on the right side, we have the function-focused approach, which reads, return $, maybe IID, comment amthus, maybe meta body. Now here's the kicker. Both of these versions function perfectly, but the newer code on the right is considered much more idiomatic in the Haskell community. It's the proper Haskell way of doing things because it elegantly passes functions around rather than explicitly stating the data variables. But as Ang argues, both of these one-liners suffer from severe readability issues. They're so incredibly brief and so dense that a developer is forced to do mental gymnastics just to figure out what data is going where. Which brings us to section 2, deconstructing idiomatic Haskell. To really understand the argument here, we need to unpack exactly why that so-called proper, idiomatic, function-focused approach is so notoriously dense. I mean, why does the right way of writing this language result in code that is actively harder to read? Well, it comes down to a couple of specific concepts mentioned by our source: point-free function and partial application. Essentially, these are mathematical shorthand techniques used in Haskell. They're designed to let the programmer focus heavily on the function itself rather than explicitly naming and passing around the data points. It is a highly symbolic way of writing. But as Ang points out, it's precisely this symbolic shorthand that creates real-world friction. It forces the programmer who's reading the code later into that extra mental translation step. You aren't just reading instructions anymore, You're deciphering mathematical symbols. It's almost like trying to translate a dead language on the fly just to fix a minor bug. Which leads us to this stark reality. Idiomatic Haskell is often mathematically sound, but it significantly impacts readability and modifiability. This is a vital distinction, and it's where the tension really lies. Look, no one is arguing that this code is broken or logically incorrect. Actually, it is mathematically beautiful. But software engineering in the real world isn't just about writing mathematically sound algorithms, is it? It's about building systems that human beings can easily jump into, understand, and safely modify without bringing the whole thing crashing down. This isn't an attack on Haskell's logic at all, but on the practical test of team-based modifiability, this hyperdense symbolic shorthand fundamentally fails because it simply demands too much cognitive overhead. So let's look at the fix in section 3, the explicit case solution. So what do we actually do about it? Ang doesn't just present the problem. Our source offers a very clear, highly practical alternative. Instead of trying to cram all the logic into a single, incredibly dense line using maybe, Ang rewrites it using a standard case statement, and this brilliantly illustrates the solution. Step 1 explicitly handles the empty scenario. Case may be meta of nothing to return body. Then step 2 explicitly handles the scenario where data exists, just meta to return meta body. By literally spelling out the nothing and the just scenarios, the need for that extra mental translation, it is completely gone. You don't have to guess what's happening. You don't have to decode point-free shorthand. The logic is just staring you right in the face. What's so fascinating here is that taking a step back and actively choosing to write more lines of code actually decreased the cognitive load. I mean, imagine the relief of a developer jumping into this code base at 2 a.m. The explicit steps make it obvious, and because it's obvious, it's safe to modify. Zooming out, let's hit section 4, the ADA philosophy. This specific code example actually points to a much larger macro-level software engineering philosophy. Ang uses this Haskell micro-case study to zoom out and talk about the fundamental design goals behind different programming languages. On one side, we have idiomatic Haskell, which heavily values mathematical soundness, symbolic shorthand, and extreme brevity, expressing complex ideas in as few characters as possible. But then you look at something like the Auto programming language. Auto was built from the ground up on entirely different priorities. It was designed specifically for industrial applications, prioritizing reliability, maintainability, and safety above absolutely everything else. Auto really doesn't care if you can cleverly solve a problem in a single line. What Auto cares about is that a developer 10 years from now can read your code, immediately understand its intent, and update it without accidentally crashing a critical system. And this brings us to a really powerful summary of Eng's conclusion regarding what makes code truly fit for industrial applications. If you're building software for the real world, where bugs have real financial or even physical consequences, and where engineering teams are constantly changing, you need to actively avoid symbolic shorthand. You absolutely must prioritize maintainability. You have to ensure reliability. And above all else, you have to write for the reader, not for the compiler, and certainly not for your own ego. That elegant, dense puzzle might feel amazing to write, but explicitly obvious code consistently beats mathematically dense code when you put it into long-term production. So, I want to leave you with a final provocative thought to take away from today's explainer. Take a look at your own projects. Look at the code you wrote yesterday. Is your clever code actually just a liability in disguise? Are you pursuing idiomatic brevity at the secret expense of your entire team's maintainability? It is so incredibly tempting to write that elegant, complex one-liner, but as we've seen today, sometimes the absolute best, most professional thing you can do for your software is to simply state the obvious. Thank you so much for joining me to unpack this concept today. Keep learning, keep questioning your assumptions, and I will see you next time.